So the next concept that we are going to discuss today is about a thread. So we know what a process is. Any program which is in execution is known as a process, and each and every process is having its own number of threads. So a single process can have any number of threads that is executing in it. So a thread is the smallest unit of execution that a process can have. It is known as a thread. So it is a basic unit of CPU utilization, and it is also known as a lightweight process. So each and every thread, it consists of a thread ID, like a process ID, like a process contains a process ID. The thread also has thread ID, program counter, register set, and stack space. This is the um, components of every thread that is present in a particular process. For example, if suppose we are having you're opening a Mozilla Firefox browser, and that is an application, right? So when you click on it and you start that application running in the background, it becomes a process. So you'll be getting a process a .exe file. When you see the task manager, you can get the process .exe, that is the Chrome browser .exe file will be available. So for a single application, through the task manager, you can view what are all the threads available for that application, and how many number of threads, how many number of processes are running, that is how many number of .exe files are running. It can be easily viewable. But for knowing what are the threads that are associated with each and every process, you need to implement a separate application which is called as process explorer and the process and threads view. So in that you can see what is the thread ID and what is the program counter contains, and what are the registers associated with each and every thread. So all these details are available in that process thread view application, and it is available open source. You can also download it and you can view that real time. So each and every thread, it contains a code section and a data section, and the other OS resources are also available for each and every thread, and these are shareable resources. So for a particular process, there may be, for example, if one process has 4 threads associated with it, all these 4 threads will be sharing the same code section, data section, and the system resources, but they will be having their own registers and stack. So this is shown in this diagram. So if you see here, this is a single threaded process. For example, the entire thing, it represents a single process, and hence here we have shared for that single process. So here we are representing a single threaded process, so only one thread is here, and the core data and files of this process is shared by this thread, and registers and stacks are available here, right? So this is a single threaded process, only one thread is present for this process, hence it is known as a single threaded process. So here this diagram, it represents a multi-threaded approach. So here a process is the same, only one process is present here, but only this one process, it contains 3 different threads here. So each and every thread is containing its own set of registers and stack. See here, so this thread is having its own register and stack, and this second one is having its own registers and stack, and the third one is having its own registers and stack. But the code, data, and the file section is common for this process. The code, data, and the files are common for all the 3 threads that are associated for this process. So such type of threads are called as multi-threaded processes. Okay, so when we see here a traditional or a heavyweight process, it has a single thread of control. So this is a traditional threaded single threaded process, and this is a multi-threaded process. Initially at older times, we were having only the single threaded approach, that is only one task can be done by the process. But here, after the multi-threaded approach's existence, we can have n number of tasks to be done at the same time by a same process. So this is the advantage of multi-threading, because multi-threading, it allows us to have multiple tasks to be completed and to be executed independently from each other at the same time. So that is the main advantage of a multi-threaded approach. So On a single processor, based upon the time switching approach, we can have multiple n number of tasks, and each task can be done by context switching. We know what is context switching in our previous lectures itself. But in multi-threaded, each and every task, it can be done, it will be doing its own execution. For example, if you are opening a browser, viewing the contents of whatever is present in the browsers is one task, and you can also download the contents from the website, that is another task. You can also chat via a chat bot which is present in that website, that is another task. And if you can also play a song which is embedded in that website, that is another task. So each and every task is associated with the opening of that particular website only. So the process is the same, but the multiple n number of tasks are present. We have now discussed 4 different types of tasks or jobs present in that particular opening of a website itself. So all these tasks are associated with that one process. So this type, everything, it happens at the same time, but as a user you will be having a feeling that everything is happening at one instant of time, but actually parallel processing is happening only by the by the use of multi-threading approach. So with multi-threading we can achieve this type of performance, and the completion of task, which is the throughput, can also be increased. So this is the main advantage of multi-threading. So these are the benefits of multi-threading, which is listed here. One is responsiveness, and the next one is resource sharing, economy, and utilization of processor architectures. So what is known as responsiveness? So as we have discussed, if if imagine that you're having only one process which is having a single thread. So it will be, if you want to open a browser and you want to download some content, or if you want to open a browser and you want to chat using that web page, it is not possible to do all these tasks at the same time at one run itself. So the system will become less responsive in that case. So when it becomes a multi-threading approach, automatically you can get all these works done with just a single click, right? So this is possible. So high responsiveness is achieved by through this via multi-threading. So this is the first advantage of multi-threading approach. So next is resource sharing. So we have already seen the each and every thread that is belonging to a process will share the data, code, and the files that are associated. Similarly, they will be sharing the resources also. So if suppose a single process is there, such type of sharing is not possible. But whereas when there are multiple number of threads available with a single process, the sharing can happen in a timely manner. In the basis of context switching, the sharing can be done in a fair way. So that is resource sharing, and automatically that resource sharing, one or the other way, the economy is also related to this resource sharing. So allocation of this memory and the resources for that process, it may become costly when in the case of single threaded approach, whereas when it goes for multiple threads, it becomes more economical. And then coming to utilization of multiprocessor architecture, imagine that you're having only n number of processes, that is n number of threads which are present for a single process, and you are having only one processor. So it is not possible to execute all the threads at the same time. But whereas when there are multi-processors are available, you have imagine that you're having five processors, that is multi-processor. Here you need to highlight the term, that is multi-processor, that is n number of CPUs are available for you for execution. But imagine that your process is having only a single thread. What happens? You cannot get the fullest utilization of all the threads, right? So all the processes, all the CPUs. So if you're having lots of, that is multi-threading approach, then you can utilize the CPU at its fullest. So each thread may be running in parallel on a different processor at that time. So this is one of the most important benefit of multi-threading. So then coming to the two different types of threads, one is the user level thread and the other one is the kernel level thread. So what is user mode and what is kernel mode, that we have discussed in the previous class itself. What is a user mode? So user mode is a mode where the user runs their applications, and it is the safest mode, and the user level programs will be executing only in the user mode. So that is what is user mode is. So in the user mode, all the thread management will be happened by the user level, at the user level itself. So the kernel will not be aware care of whatever is happening in the user mode. So the thread library, it will contain the code for creating and destroying the threads, and the message passing, and the sharing of data, context switching, everything will be happening only in the user mode in case of user level threads. At the same thing, when it comes for kernel level thread, the thread management will be done by the kernel level. So it is the most privileged mode. As we know, it is a highly secure mode. So directly the OS involves in this mode with the kernel threads. So the kernel threads are slower to create and also to manage when compared with that of the user mode, because in user mode we will be doing everything in the application level. So that is what an user mode and the kernel mode is, the difference. So in order to have a good communication between this user mode and the kernel mode, the so this is the difference between the user level thread and the kernel level thread. So here we know it is a safer mode, so definitely the processes will be faster when compared to the kernel mode, and in the kernel mode will be having very slow process, and because OS is directly involved here, whereas here the OS is not directly involved, and only the user level of applications will be handling, and it will be managing the user level threads here. So this is the difference between user level mode and the kernel level. But only if there is a communication and if there is a managing happening of proper flow between this user level and the kernel level, a process can be completed, because if anyways the user level application needs the OS resources for better execution of it. So definitely that should be done in a smoother way. So for that purpose we are going for three different models in multi-threading. One is the many-to-one model, then next one is the one-to-one model, and many-to-many model. So with these three approaches we can have a good communication with the user level. That is the way the user level thread it communicates with the kernel level thread. It is based upon only these three multi-threading models. So we can see one by one how these three types are having, what are the pros and cons of these three approaches that we can see from one by one. So the first one is many to one model. So as the name indicates, here there are many user level threads and only one kernel level thread. So here the you can, from the diagram you can clearly see that there are n number of 4 user level threads are present here, and only this round represents this kernel. So the for example, for a single process we are having 4 user level threads, and everything is connected to only one kernel. So what is the cons here means, if suppose this user level thread is executing a block system call, any one. For example, imagine this user level thread is executing a block system call. Automatically everything is commonly connected to this one kernel means, so if suppose a single user level thread is executing a block system call, automatically it will stop the entire process, and it will in turn affect all the 3 user level threads which are present here. So this is one of the main disadvantage of this user level thread, this type of many to one model. And also only one thread it can access the kernel at a particular instant of time. So parallel processing is also not possible. So multiple threads are unable to run in this parallel processor. If in case of multi-processing it is not possible. We have only one kernel here, because if it is only one kernel, then only one processor will be used by this entire process. Even though user level threads are many in number, we have only one kernel, so only one process will be used at a time. So the efficiency and the utilization of this multiprocessor architecture is also very low in case of many to one model. So in order to overcome this disadvantage, we move to the next model, which is the one-to-one model. So in one-to-one model, each user level thread is connected to each kernel level thread. So it provides more concurrency than the many-to-one model by allowing the other threads also to run. If suppose one thread executes a block system call, as we have seen in the last case, even though one user level thread is executing a block system call, that blocking will happen only for this kernel, and it won't affect the rest of the other kernels. So this is one of the main advantage here. Also, it allows multiple threads to run in parallel and on multiple processes. Imagine that you're having four processes, that is a multi-process system. You're having running with a multi-process system, and you're having 4 processes in hand. So each of this kernel, it will be able to execute execute in each of the processor. So creating user thread, it requires what is a disadvantage is every user level thread, it should be associated with its kernel level thread, so it will be highly economically too costly. And also the overhead of creating this kernel level thread, it can burden the performance of the entire application. And most of the implementations of this model, it restricts the number of threads appropriately to the system. So this is the main disadvantage of this, going for this kernel level thread. But comparatively to many to one model, one to one model is less complex. So moving on to the next model, which is the many to many model. So many to many model, here many user level threads are there and many kernel level threads are there. So here multiplexing, it will happen many user level threads, up to 4 user level threads are here and 3 kernel level threads are here. So here one to one approach is not possible here. It solely one user level thread is not connected to one kernel, and multiprocessor architecture utilization is also possible here. So the number of the, num the number of kernel threads, it may be specific to either a particular application or a particular machine. So developers can create as many user threads as necessary, and the corresponding kernel threads, it can run in parallel on a multiprocessor. So utilization of such processors are also possible, and the blocking of a system call, it will not create the entire system to crash. So this is the best model comparatively of all the three. So with this, we come to the end of what are the different types of threads available, and with this we can end up this session, and the next session we can continue the next topic. Thank you.